It's really fun to be back here. Dimex was actually the first place where, the first workshop or conference that I ever went to. And so you're the reason that I'm stuck in this profession. So I'm going to talk about exploration into algorithmic fairness, a joint work with my student Andrew Morgan. And this is still a work in progress. So I'd like to keep this as much as possible as a dialogue. The technical results haven't really changed so much in the last few weeks, but the interpretation that we have of them is changing basically on a daily basis. So please do interrupt me as much as you can. So this is going to be a talk about classification. So classification happens all the time. We would like to assign individuals with some outcome based on some data we have. And we do this all the time. Credit card applications, criminal sentencing is a kind of a big area where this happens now more recently, targeted advertising, and so on and so forth. And the question that we're addressing is, what does it mean for such a classification to be biased or discriminatory? And in particular, what do these words of biased or unfair mean? So that's what we're going to try to address. But before I do that, let me start off with a real-world example that really blew up on the internet last year. So there was this very interesting tool called Compass that is used in criminal sentencing. So this is a tool that uses big data in order to look at some features of suspected criminals, and based on these features output a score. And this score should more or less indicate whether these criminals will recidivate. So will they commit a crime in the next 6 months or so, let's say. And later on, this score has been used in various different ways, for instance, in pre-trial sentencing or bail setting and so on and so forth. And so this recent study from last year by ProPublica went over this tool and data and suggested that actually this tool is discriminating against minorities. And in particular, their claim was the following: while black defendants, they had a higher rate of recidivating on average. But even if we adjust for this difference in the base rate, actually they are 45% more likely to get a higher score than whites. So it's a huge gap that they're claiming, and therefore this algorithm now is somehow implicitly or explicitly, we don't know, biasing against black defendants. So how do we prevent against these type of issues? So to do that, the first thing we need to do is to have a good definition of what does it mean for an algorithm to be fair. And once we have that, the next natural question is, can we remedy the situation, and can we sanitize unfair algorithms and unbias them to make them fair? So to exemplify this process, let me look at something slightly less controversial, which is, and also something that's more familiar to us, paper reviewing. So, so we have a set of individuals. They're going to be sampled from a distribution. These are papers. Okay. These papers, let's say this is not a very selective conference. There are, in fact, journals like this. They will accept things that are correct and should reject things that are wrong. Okay? If it's correct, then you. So this is something objective, right? Is the math correct? If so, accept it. Otherwise, reject it. So that's the class of the individual. So now the class is just a function of the individual sigma. And now we have some classifier that gets to see sigma, maybe a subset of it, maybe some, well, it gets to see some part of this individual. And based on this, it needs to output some score that's intuitively, if you get a high score, you're likely to be a correct paper, and low score, you should be likely to be an incorrect paper. Okay? And so here we have an outcome space and outcome space if 1 to 9. Now, we also have different groups of the individuals of the papers. And this is an example by the student, Andrew. Andrew has a strong belief that, faculty and students are treated differently in the reviews. Okay? And so the group here of the individual is whether you're a student or faculty. So this is Andrew, that is me. And so we'd like to see whether this classifier is biasing against or students or against faculty. Okay. So let's say Andrew here. What he does is that basically whenever you have a paper by a student, he's going to give it a high score. That's the classifier. And whenever it's a paper by faculty, they give it a low score. That's clearly very discriminatory in some sense, right? Intuitively, it's biased, right? So, natural approach would be to say, well, the classifier is not allowed to look at just look at this attribute whether you're a student or faculty, right? And this is something we do all the time, right? We do these blind reviews. We remove the name. Is this good enough?
No, because it could use like part of the sentences, complete and grammatical. I'm not sure that's actually.
That is to bias against who, right? Yeah, so of course you can't because they're very different. There are a lot of different other things that are correlated with whether you're a student or faculty, and we can just look at those features. So it's really hard to remove all those features. Okay? Now, so this is one approach that we're trying to go, not trying to like somehow relaxed or trying to restrict what this classifier is doing. Another approach would be to just try to say, what is perfect fairness? So here is something that intuitively should be perfectly fair. If I have a classifier that is perfectly correct, right? In the sense that whenever it's a correct paper, he says 9. Whenever it's incorrect paper, he says 1. That is as fair as it gets, right? Everybody agrees? Okay. There is no bias. We're really just basing our decision based on, you don't agree? You were in...
Well, okay. We can take that as a definition.
Right. It's a, no. So I claim that this is, perfect fairness. But of course, perfect fairness, if you define it this way, require, a perfect prediction. That is very rare. We very rarely have machine learning algorithms that are just able to perfectly predict exactly the property you're trying to do. That is the whole problem. Basically, it never happens, right? Even if we sometimes can succeed with high probability, it's not the case that we always succeed. Here's a few other approaches that people came up with. And there was this very nice paper by Dwork et al. From ITCS 2012 that introduced this notion of statistical parity, which is actually very closely related to a notion of causal total effect introduced by Judea Pearl quite 10 years even earlier. And here the idea is just to say, I would like to make sure that when I run the classifier on faculty and students, I'm going to get the same distribution of scores. Okay? That seems very natural. So look at the scores, the average scores, let's say that faculty get, the average scores students get, and they should be close. Of course, the problem with this definition is that it doesn't take into account the fact that there are differences in base rates. Right? It could potentially be the case, I don't know, right? That maybe faculty actually write better papers than students, right? Or vice versa, who knows, right? And if so, then this is just not fair. If we require something like this, then we are actually biasing against the group that writes better papers. So that doesn't seem right either. Okay. So now let us, in that case, turn to our first way of formalizing the notion of fairness, which is actually a notion that's very, very similar to a few different other notions people have been looking at, and tries to capture more or less what the ProPublica article was suggesting that the Compass classifier didn't satisfy. So the first thing is what we call fair treatment, which is simply the idea to say that individuals in the same class, so individuals in the context of papers that are actually correct should be treated the same way no matter whether they come from faculty and students. So take correct papers, Sample a random correct paper by a faculty, a random correct paper by a student. If so, I would like to make sure that the outcome that we get are closely are similar. Does it make sense? So a little bit more formally, we said as classifier satisfies fair treatment. If for any class B, so this was a correct paper versus a false paper, take any two groups, students and faculty, the distribution of the outcome of the classifier conditioning on the class being this and the group being X should be close to the same the output of the classifier when I condition instead of the different class. Okay? And when I say close, I mean close in multiplicative distance in the same way as we defined it for differential privacy. Okay, and that turns out to be very, very important. So as I mentioned, this is very similar to a few other definitions. In particular, Clymer et al. In this very nice paper from last year called something like this balance, and Moritz et al. Called something like this equalized odds.
Moritz, the last name.
Oh, sorry, hard to, yeah, okay. I have it right later. It could be, you know. The difference in their definition and ours is that they only require these distributions to be close in expectation, and we're actually looking at the full distribution and looking at this multiplicative distance. And I won't have time to go into why that is the case, but in this crowd, the reason why we would like the closeness of the distributions and also why we want it to be multiplicative is exactly for the same reasons as for privacy. Okay, so does this definition make sense? So fair treated means that if I take correct papers by students and faculty, the output, the distributions of the output should be close. So, okay, let's go over a few different examples of where we're applying this thing and what it means. So the first one is frisking. So the police wants to frisk people in the street based on maybe some attributes that they've seen. Maybe they have some cameras that see whether you walk in a funny way. I don't know what. And so in the case of frisking, what we would like to, for instance, is that black and white suspects who actually carry a gun should be searched with roughly the same probability. Okay? Because it could be the case that the base rates, the probability of carrying a gun is different among the races, but if you actually carry a gun, you should be frisked with the same probability. Okay? Another example is hiring. So hiring of male and female doctors. And let's say that there is a bit saying whether you're a competent doctor or not. Okay? The situation obviously is more complicated, but let's say there is just a bit determining that. If so, you want to say pick doctors that are competent. Men and women should be actually hired with roughly the same probability, condition on being competent. Right?
So for the frisking example, or in general for your definition, do you want that to hold for all the classes? So black and white suspects who don't carry a gun are
yes,
also...
Yes. Yeah. So here I'm just, it should be both, yeah. So if you carry one, and if you don't carry, it should be the same probability, yeah. Definitely.
Because, like with the equalized odds definition, there's also, I think, like equalized opportunity, kind of the one-sided version.
Yeah.
Of that.
So I consider just
kind of
both sides. Yeah,
both sides.
exactly. Yeah. And in compass, as I mentioned, this property is the exact property that doesn't hold because we're treated differently. So what I would argue here, and you can argue back with me, if we don't have this property, then we're actually explicitly biasing in some way. The classifier is biasing. Okay? The classifier treats different groups differently, even conditional on having the attribute that we'd like to classify on. Okay, let me move on now to a different way to look at fairness. And this is what we refer to as fair predictivity. And this notion tries to capture the idea that the classifier should be equally predictive across groups. Okay? So, okay, I guess I missed, I deleted the wrong slide. So equally predictive among groups, that means that we basically flip the conditioning. So look at the distribution of whether the individual actually is in the class, or the actual class of the individual, condition on the classifying outputting a certain outcome. So let's say papers that have a score of 8, what is the probability they're actually good if they're written by faculty versus written by a student? So this notion requires these probabilities to be close. So if I have a paper that gets a score of 9 that's written by a faculty and written by a student, the probabilities that they're actually good papers, correct papers, should be similar. Does it make sense? So okay, here in this example, the paper got a score. Papers that get a score of 2, the distribution of whether they're actually correct should be the same across groups. Okay, so let's go over the examples again here that we had. So let's look at frisking. So what this means in the case of frisking is that out of the people I frisk, okay, so look at the people you frisk. We have a similar fraction players, people that actually carry a gun, whether I look at black suspects or white suspects. Right? It clearly would be unfair if among the people I frisk, it is the case that 90% of the white suspects have a gun and only 10% of the black suspects have a gun, because in that case, I'm over-frisking black suspects. Right? So this requires that it should be equally predictive on both. So this is a more subtle definition, and actually the compass tool was built in order to satisfy something like this. We wanted to make sure that we get the same predictivity on both. Yeah?
So, suppose I've got a classifier that closes its eyes and makes a prediction, a random, just predicts a random bit.
Yeah.
Okay.
I'll get to these type of examples. Yeah. So this definition, it will be bizarre whether we want to require something like this.
So I guess if I understand this definition, it has the advantage, such as it is, of being you can evaluate it empirically.
You can evaluate both empirically. Both of them can be evaluated empirically.
It's much harder to evaluate.
No, you have usually have the whole data.
First one, because you've got a counterfactual. Like, say, let's say frisking, right? How do you know how many people?
This counterfactual thing is an issue, but there are various different ways you can get around it. But let's say you have data that's actually with the random samples with the class in it. In that case, you can evaluate experimentally. And there are other methods also, even to deal with that, even if you don't have it. But yeah, so the intuition just is to say, whenever this thing gives me a particular score, then it should actually be equally predictive across the two races. Okay. And at first, we had the same kind of opinion as you, that this is kind of as Adam, that it's harder to understand what this actually means, and whether this is, well, it seems natural to say that, other people I frisk, it is the case that I should have an equal fraction, right? But here is an argument that I think is rather convincing of why we need something like this. Okay, so this is not about an explicit bias in terms of a classifier, but what I would like to argue is that if a classifier doesn't satisfy fair predictivity, okay, in that case, others that use the outcome of this classifier will bias against the group. Okay, so let's see that slowly. Let's look, for instance, on the compass. Let's say there was the case that for white defendant, whenever this thing outputs a score of 9, it actually only is it's 45% probability of committing a crime, whereas if for black defendants, when it's output a score of 9, it's 65. Okay, let's say that it has different prediction rates. Okay, if so, the judge that gets these scores, what should a rational judge do? He clearly should try to bias them against black defendants, because he looks at the score. Take two people who have the same score, he will try to bias that back. That would be a rational thing to do. Does that make sense? Maybe a better explanation is an example that I heard from that John Kleinberg suggested when he heard this thing, which was, let's look at the hiring. Okay, we're hiring male and female doctors based on a classifier that doesn't satisfy fair predictivity. That means that when a classifier says hiring, it could be the case that with 60% probability a male doctor is good, whereas women may only be good with 40% probability, let's say. That would be what it means to have a gap in fair predictivity. If you come in as a patient into the hospital and you know that the way the hiring has been done is in a method that doesn't satisfy fair predictivity, whenever you see this a doctor, you're going to try to not use a woman doctor. That would be a rational thing to do, because condition picking a random woman doctor, if you have these conditions, then you know that it's only 40% probability that she is competent. So unless you have this thing, you're going to get this post bias where people that use the outcome of the classifier will bias against certain groups. Yeah?
This also can, in practice, easily work into a feedback bias where future development of classifiers
Will be
are biased.
Yes, yeah, exactly. So that's my point is, like, if you don't satisfy this thing, like maybe the classifier itself isn't explicitly biasing, but if so, the way you use the outcome of this classifier, the way people will use it, they will be forced to bias also. So even if you don't buy that this is something that's desirable, I think this is a convincing way to say that the data will be used in a biased way. Okay, so I don't have that much time, but of course the natural question is, can we achieve both of these at the same time? There are two degenerate cases when you can do it. The first one is when the base rates are identical. If so, when the base then it's trivial to achieve it. Another approach, another observation is when you have perfect prediction, then again it's trivial to achieve them. So if your classifier actually is perfect, then you can do it. But these are really just the trivial conditions. When you have the same base rates, one trivial way to achieve them is just to output anything. That's going to be very fair, because the base rates are already fair. But the challenge is there a way to achieve a classification that works even if I don't have perfect prediction? It doesn't always work, and the base rates are different. Okay. So there were a bunch of prior work on this, all from last year. The first one is Choldechova, and she shows that for the case of binary classifiers, if you want to achieve both of these notions in the perfect case, where epsilon is equal to 0, then that's not impossible. Okay, and this is basically a two-line proof. It follows directly from conditional probabilities. Okay. But I guess this is not very helpful when talking about compass, because it only deals with the case of binary outputs and binary inputs. And in compass, there was a score. And second of all, the case of epsilon equals 0 maybe doesn't tell us much about epsilon is equal to greater than 0. Just as for differential privacy, we know that nothing non-trivial can be achieved when epsilon is equal to 0. But when epsilon is greater than 0, we can do a lot of interesting things, right? So obviously, we'd like to see what happens when you relax it. And then there was this very nice work by Kleinberg et al. So they focused explicitly on risk assessment, such as in compass, when this classifier needs to output a score. And they show that anything that satisfies, well, that it's impossible to satisfy epsilon treatment, and another notion called calibration at the same time. So what is calibration? Calibration is not a fairness notion. Calibration is instead an accuracy notion. Okay? And calibration says that whenever this classifier outputs a score of 3, in that case, it should be the case that 30% of the people for which it outputs 3 actually are good. Okay? So it's kind of an accuracy saying that the scores really are well calibrated or accurate representation of the outcomes. Okay? And this, of course, is a desirable thing, like for scores to be correct. So what they're saying is, if these scores are actually correct, then you cannot satisfy fair treatment at the same time, except in the case when you have perfect prediction or equal base rates. Okay. I'd like to point out that this calibration is a strictly stronger property than fair treatment, because they require calibration, they could require calibration condition on the different groups. So whereas fair predictivity just says that we're equally predictive, it doesn't have to be accurate necessarily. Does that make sense? He's saying that actually for both groups it needs to be accurate. Fair predictivity just says it needs to be equally predictive. Now we know that calibration is not always easy to achieve. In particular, like if you look at the weather forecasts, they're usually not calibrated. Right? It's not so easy to get a classification that's calibrated. It's whenever it says 30%, on the days when this thing outputs 30%, it rains 30% of the time. Right? That's what calibration means, and that's not always easy to achieve. Also, another thing to note here is that calibration, if you look at binary outcome, that's actually equivalent to perfect prediction. So it's kind of a degenerate definition when you look at binary outcomes. All right, so, yeah?
Sorry, for the last point, can't you always just predict the base rate, which would not be perfect? Like for the weather example, I mean,
yeah, exactly. Something that's calibrated, yeah. So always outputting base rate is always calibrated, yeah.
That's not perfect predictions.
That's not perfect prediction.
I mean, that would be like if it rains 30%.
But that's not going to be, I'm not sure that's going to work because you also need to condition on you want a calibration condition on the two classes also. But I guess you could do that. I'll need to think about it, yeah. Thanks. Okay, so our main theorem is showing that you cannot achieve these two together, except in the case that the classifier satisfies something called subgroup perfect prediction. So what is subgroup perfect prediction? That means that there exist I can bundle together sets of groups so that the classifier can perfectly tell apart these two groups. So in the case of just two groups, like we had faculty and students, this is equivalent to perfect prediction. But more generally, it's not. Okay. So I guess I don't have much time. I was thinking of going over I'm not going to go over any of the proof. It's very nice pictures the student did. So the question now is how should one interpret this result? And I guess it's not clear. We need to give up on one of these properties, right? We need to either give up on, we need to either kind of, if the base rates are different, we either have to be explicitly biased in the classifier, or if we're not, then people after the fact will bias. So it's kind of like this, if you don't have equal base rates, it's very hard to get away from this, the bias. So it's kind of disturbing. So the approach we pursued in the paper is to say, well, explicit bias is worse than what happens afterwards. So we're going to try to prevent against that. So the next question we addressed is there a way to sanitize an unfair classifier into a fair one? And here, when we say fair, in that case, we mean just satisfying fair treatment. And this is a question that's very closely related to one investigated in the paper by Hart et al. And they consider this notion of sanitization called a derived classifier.
Is it true that you are biased against words because you can never spell his name right?
Didn't I? Never? Maybe, yeah.
No, there was at least one occurrence of his correctly spelled.
Okay, yeah. I just have a lot of diversity in the spelling of names. That's like, you need to randomize. So Hart et al. Consider this particular, okay, all right. I'll give you 30 more. So they consider this a very nice approach to sanitizing a classifier by post-processing it. So I have some original classifier that takes some data, outputs something, and I can create a derived one which only looks at the output of this thing and also the group of the individual, and then tries to, like, whenever this guy says something, it maybe randomizes a little bit over it. So it's randomizes over the output somehow. And the question is, can I, by just looking at the output and the group, remove the bias in a classifier? And they show this very nice result that actually the optimal fair derived classifier in this way can be found as a solution of an LP. The only issue with this LP is that to set up this LP, you need to know a bunch of parameters of the underlying distribution, and you need to know a bunch of parameters of the classifier. It's not clear how you can achieve them, how you can get these things. So what we show is we presented a notion of black box sanitization, where I would like to take a classifier, use them as a black box, take the distribution, only use them as a black box. In fact, just taking a bunch of samples from training data and seeing the output of classifying on that training data, and see, can I, using just that, obtain a derived classifier that's going to be fair. And indeed, that's our second main result. We show that whenever the outcome space is polynomial size, if so, we can find an epsilon fair derived classifier that is very close to the optimal fair derived classifier. Not going to go into how that is done, but the point is you can implement it. The student implemented it. He ran it on the data, and it turns out that when doing that, you lose very little in accuracy. So the derived classifier satisfies epsilon fairness and doesn't loses only 2% in accuracy, or
Fair treatment, right?
for fair treatment, only fair treatment, yeah. And it's actually also very close to the original one on average. But sometimes it's going to do more crazy things. So in conclusion, we introduced these two notions of fairness that kind of just formalize things that were discussed either implicitly or explicitly previously in literature, but we define them in a somewhat more formal way, and using ideas from the definition of differential privacy. And then unfortunately we show that simultaneously achieving them is impossible. And now that leads to the question of what do we do? So we took one approach, which was trying to stick to fair treatment, and we showed that actually you can take any unfair classifier and sanitize it, massage them into something that's fair, as long as the outcome space is sufficiently small. Thank you.
Unfortunately, we're tight for time, but maybe we can take one question before we move to the next speaker. Yeah.
If you relax one or both of your definitions in a similar sense of various relaxations of different.
Yeah, that's a great question. In fact, impossibility breaks down.
Yeah.
Okay, so I think an epsilon delta version, we don't know. Basically, it seems impossibility breaks down, and that could work out. And if you take that kind of this game theoretic interpretation, I have fair predictivity. If the only thing you want is an epsilon Nash equilibrium where epsilon is additive, maybe I'm speaking too fast here, but if so, such an epsilon delta definition would be good enough. And so that might be fine. I'm not sure, though, whether it is appropriate or not, because having these gaps that are small additively might be very dangerous when the probabilities are very small. So it's not clear whether that's fine or not.
Here, the game theoretic, the question is it like a reasonable response to the situation to simply take the classifier's output at face value and not try to adjust it? Is that that's the strategy you want to argue?
You would like to argue that just taking,
exactly.
Exactly. And so it would be an epsilon equilibrium if you use epsilon as an additive thing, but maybe that's the wrong thing to do, because now you're in this conditional, so just like with differential privacy, you want to, maybe the epsilon delta.
We're not going to start the next talk without you, so yeah.
So I wonder if there are some connections between your approach to sanitizing classifiers and some recent work in the security community on adversarial examples. Do you think these types of sanitized classifiers that you're developing will be more robust to evasion attacks?
I'm not sure. That's a very interesting question. I don't know. It's not a trivial thing to answer. Sorry.
Yeah. So let's thank Rafael again.